Welcome to our podcast. I'm Sivakumar, embarking on an exciting journey with Mr. Sivakumar, the visionary founder and CEO of Maven Silicon, where we delve into the dynamic world of technology and just, decode how exactly vlsi seamlessly fits into our everyday lives. So tell me, Mr. Sivakumar, what do you aim to bring in today's conversation and just the podcast in general?
In our life, we use various kinds of electronic devices and we also try different kinds of technologies. So in this podcast series, I am going to explain to people like you who are very curious about knowing all these things. For example, you might be wondering how a smartphone works. What could be the difference between smartphone and laptop? We do various things on cloud computing systems and how this technology works, cloud computing. There could be different things like 5G, artificial intelligence, autonomous vehicles. On top of all these things, I want to explain to the passionate engineers who want to build their career in the semiconductor industry how our ecosystem operates, what is semiconductor ecosystem. And to know everything about semiconductors, they need to understand the technology, VLSI, very large scale integration. When you talk about VLSI, there could be many things like ASIC, application specific integrated circuit, FPGA, field programmable gate arrays, the difference between ASIC and FPGA, system on a chip, ASIC design flow, how we use ASICs, how we use FPGAs, and using all these things, ASICs, FPGAs, SoCs, chips, how we build devices like smartphones. That's what I'm going to explain to curious engineers or passionate engineers who want to build their career in the semiconductor industry.
Great to know. Just a small introduction. Mr. Sivakumar, with over 25 years of experience in academia, semiconductor industry, electrical engineering, his knowledge is unparalleled too. And I'm just here as an undergraduate student, hoping to bring some fresh perspective to today's conversation and probably an insatiable curiosity to fulfill for today. So, shall we begin with our first episode?
Absolutely.
So, here we go with our first episode. You're probably watching this podcast or listening to it on your smartphone. And here's a friendly reminder for you to probably kill those applications running in your background. So as a student, I'm always someone who's into my phone. I'm watching Instagram, I'm editing PDFs, I'm making documents, taking videos, editing videos. So I'm 24/7 on my phone. So I want to understand how exactly do these sleek devices run such complex tasks like browsing the web, taking stunning pictures continuously.
Right. So basically you want to know how this smartphone works, right? For example, you look at iPhone 14. There is a complex SoC, system on a chip, called A16. This chip is very complex. It is using various kinds of components like processors. A16 chip has 6 ARM CPUs, central processing units, and 5 Apple's GPUs. It has got 16-core neural engine. You may have this question, why neural engine? So I can correlate with CPUs and GPUs. CPU might be required for running applications and GPU might be highly needed for running video games. But what is neural engine? Neural engine is required for AI applications. For example, if you want your smartphone to understand your language, you can also call Siri to do various things, right? So that could be one example why you need neural engine, which is very complex. So it has CPUs, GPUs, 16-core neural engine. It has image signal processor. It has display engine. Like this, there could be hundreds of components. We call these components as intellectual properties. That's why this chip is so complex, it demands 16 billion transistors. So the question is, why VLSI? Very large scale integration. It's all about packing all these transistors into a small chip. If you want your smartphone to run multiple applications, many applications, millions of applications, then the device should be very powerful. If you expect the device should be very powerful, then the chip is important. What is inside? That's like brain. It does everything for you. Whatever you do on your smartphone, basically the chip is going to do that. Then how it does? That's what I want to explain. If I can explain everything like a story, people can enjoy, but what the engineer wants, fundamentally, how everything is going to happen in terms of binary. We speak language like English or various other languages, but the electronic devices can understand only binary, zeros and ones. So the phone is going to process everything in terms of binary, zeros and ones. Okay, now you look at your smartphone. You take simple application, calculator, right? What do you do with calculator? You do various things like addition, multiplication, right? For example, you say something like 4 plus 6, then it gives the answer 10, right? Then how it does, that's what I want to explain. Calculator is a mobile app. We use high-level language like Java to create this kind of application. Then what happens is we convert these applications into binary. That's how basically the smartphone stores all the applications you take. YouTube, Facebook, Instagram, calculator, everything is stored in terms of binary. How do we convert the high-level language into binary? You might be familiar with languages like Java or C, C++, right? So you might be enjoying writing the source code. You might prefer languages like Python. Fine, no issues. That's like how you use high-level language to create these applications. You have created, you are a software programmer. But how can I run this application on this smartphone? That's what I'm trying to explain. So what we do is we convert your application into binary. For example, if the smartphone uses ARM CPU, then we convert your application into ARM machine language. So there is a process. We use various tools like compilers and assemblers. Through that process, we convert your high-level language into machine language. When I say machine language, that is nothing but the instruction set for the processor. See, whatever you define in your software program, eventually everything will be executed in terms of instruction. For processor, the instruction could be like add, multiply, divide. That's how everything is going to unfold. Now, this simple application, you look at calculator, it is pretty straightforward. When you say 4 plus 6, the processor is going to execute an instruction called add. So it is going to add 4 plus 6. When it produces that value 10, the application will take that result and displays on your mobile phone. So internally, it is going to process everything in terms of CPU's instructions. In this case, ARM CPU. So the application is stored in terms of binary in the storage memory. Then you have this operating system, right? This iPhone has operating system called iOS. So when you click on an app, the operating system loads the binary into random access memory. So it transfers the binary into RAM. And immediately the starting address of the RAM is stored in a register called program counter. So CPU, Central Processing Unit, has a special register called PC. So the starting address of the memory is stored in PC, and the PC is going to increment. It depends on the addressing mode. And based on the PC value, the processor is going to fetch the instructions sequentially, sometimes non-sequentially, and then it's going to execute the application. So when you say 4 plus 6, based on the PC value, it's going to fetch the instruction and it's going to do addition, and then the processor is going to produce the value 10. Then eventually your application will get the result back, and that's how you're going to get the result. This is how fundamentally everything happens within the chip. Why I'm explaining this? This kind of understanding is highly needed for the electronics engineers who want to be part of the semiconductor industry. Whether you have done VLSI course or not, when you look at any device like smartphone, you have to ask yourself some of the basic questions like, what kind of chip is used? What is A16? Why it is so complex? How many transistors are there? How did we pack 16 billion transistors into this complex chip? It's based on 5 nanometer technology. That's where technology becomes important. So when you ask yourself these kind of questions, then you understand, okay, this is how basically we use technology. This is how we build smartphone. This kind of curiosity is highly needed. So fundamentally, this is how smartphone works.
So you mentioned the term SoC, and that prompted a question in my head. What exactly is SoC, system on chip? And why do phones rely on SoC so much? And why not any other simpler architecture?
Right. Smartphone. We have been talking about smartphone, right? Smartphone is very different from laptop. In terms of complexity, whatever the laptop does, you might be able to do almost everything on smartphone itself, equally powerful. Okay. But smartphone is highly portable, and power consumption, if you look at it, cannot consume so much power because you always think about the requirement, like how often I am going to charge my phone. If you end up charging your phone every 1 hour, you might not prefer smartphone, right? So you might want to charge your smartphone maybe once in 3 days. But actually in your life, how often you charge your phone?
My phone's always at 10%, but usually I charge it once or twice a day at maximum.
Right. See, basically we design smartphone in such a way that it doesn't consume much power so that the consumer can charge the phone maybe once in 2 days, once in 3 days, but still everyone charges their phone at least once in a day because they use smartphone extensively. It doesn't mean that it consumes so much power. You use smartphone all the times. You do everything on your smartphone. That's where you need to think about your lifestyle. How often you use your laptop, you just think about it. Slowly you are moving away from your laptop, right? So power consumption is critical. So 2 things are important when it comes to smartphone. It should be highly portable. It can't be bulky. It should not be like laptop. You should be able to carry the smartphone in your pocket. It should be a portable device. At the same time, it should consume less power. That's how smartphone is different from laptop. So here, we can't use the same kind of electronic circuit for smartphone. You look at laptop, there could be a complex circuit board, PCB, printed circuit board, and the PCB may have multiple chips on it. That's how we build laptop. Because laptop is different. It doesn't have to be highly portable. It doesn't have to be very small. It doesn't have to be sleek, but here the requirement is entirely different. So I can't use the same kind of circuit board for this smartphone. So we look at like how to realize this kind of system on a chip itself. So what I'm saying is, if you want to have a complex electronic device, basically you need to design a complex PCB, printed circuit board. There you think of having multiple chips, complex chips. That's how we build electronic system. Here, how I look at it is, instead of designing a complex printed circuit board, I am thinking of converting this complete PCB into a small chip. That's where VLSI comes into picture, very large scale integration. So every time when we look at a complex device, something like DSLR camera or projector, I dream of combining all these devices into my smartphone. Maybe in future, I would like to have projector also in my smartphone. If I want to explain all these concepts, I just want to put on the projector and then show everything on the screen with animations, right? So it's all about like integrating various devices into one device. If I want to do that, again, I need to look at what is the circuit inside the projector. Then I will think of converting that circuit into a small component. Then I will think of having the small component as part of my chip itself. This is like integrating all kinds of devices into one device. That's why we need system on a chip. System on a chip means you try to realize the entire system on a single chip itself. System on a chip. You don't really need printed circuit board with multiple chips. That's why we prefer system on a chip. And when we pack all these things within a chip, it increases the performance. So we look at 3 parameters: power, performance, and area. Power consumption should be very low. We don't want to charge our phone every 1 hour. Performance is critical. Nobody's going to run all the applications one by one. Okay, now I'm sending some message on WhatsApp. Let me kill WhatsApp and then I just want to watch some movie on YouTube. Fine, now I'm going to listen to music. Let me kill YouTube. No, you're not going to do that. You will switch between apps. You think about various scenarios. For example, you book a cab on Uber. Then you use Uber app. And then the cab comes. You get onto the car. And then while traveling, you might be wondering like, okay, how about watching a movie? And then you might be watching a movie on YouTube. And suddenly you think like, okay, this is kind of boring. Let me talk to my friend. Then you might want to call your friend. And then suddenly you think like, okay, fine. Now I just want to check my status on Facebook. I just want to tweet. So you would be doing various things on your smartphone, right? So performance is very critical. The third thing is area. Power, performance, and area. Area is very, very important. I want to make sure that the chip is going to be small as possible. Then only I can think of making this device portable. So I'm super ambitious. I want to pack all the chips into a single chip. At the same time, I want the chip to be very small. It's going to be very, very difficult. That's why we need very large scale integration.
I understand how you explain why we need VLSI. And it's very exciting to, imagine how beautifully you've explained how important SOC is. I want to understand, how does your course come into picture? How does it help me understand the making of a smartphone?
Fine. Young engineers, electronics engineers who want to deal with VLSI, usually they come to Maven Silicon. But you go to any VLSI training company like Maven Silicon, they may have standard curriculum. It might start with a basic module like digital electronics, and then they will take the engineers through various other modules like Verilog, System Verilog. That's what happens in the college. You just think about it, how their journey was in their engineering college. They had various modules. They understood various concepts, but they had one big question: what I'm going to do with all these concepts? So it's about how they can connect all these dots and understand the big picture. I know how to create circuits. I understand digital electronics. Now the circuit is there. I know how to use a programming language like Verilog. I know how to convert this circuit into a source code, and then I know how to synthesize this source code into netlist. Fine, all these things are fine. But what are you going to do with all these things? There is a flow, design flow, and you do various things, but eventually how you apply all these concepts to do something meaningful. And what is that? That's how my code starts. So I show them like, hey, this is smartphone, iPhone 14, and there is a chip inside, SoC, system on a chip. It's A16. When I say A16, 16 billion transistors. Why it demands 16 billion transistors? Let's dive deep into the architecture. I want you to understand how we build this system on a chip. What are the various components like CPUs, GPUs, display engine, image signal processor, encryption engine, and various interface IPs, and how we use on-chip bus to connect all these IPs together, how we build this chip, and then how we do various things on the smartphone. When you click on an app, eventually how the processor executes everything in terms of processor instructions. That's what I want every engineer to understand, the big picture. Once they understand, wow, this is how we build smartphone, and now I want to understand how we can apply various concepts to do various things like how I can build circuit, how I can convert the circuit into source code, and then there could be other things like synthesis, physical design, and then finally routed netlist, and how the netlist will be shared with the foundry, and then how the foundry fabricates the chip. That's fine. But they need to understand the big picture. Why VLSI? How we use very large scale integration to build system on a chip. And that's how I teach at Maven Silicon.
So you're telling students like me have to dive deep into whatever we're learning. So I want to know, as a student, how does learning about smartphone technology really benefit my knowledge and my career prospects in the tech industry?
Smartphone is an example, just an example to understand the big picture. But at the same time, if you want to build your career in the industry, you might want to choose companies like Samsung. For example, you are going to be part of Samsung or Apple. Basically, they build mobile SoCs because they create smartphones. To design smartphones, they need to design system on a chip. So if you are going to be part of companies like Samsung or Apple, obviously you are going to deal with mobile SoC design. So whatever you learn about smartphone and system on a chip, that's going to be useful. But at Maven Silicon, what we actually focus ASIC design flow, how you deal with various things. If you look at ASIC design flow, it starts off with specification. What is specification? You need to understand everything about the chip. And then once you understand the functionality, then you need to create functional model. Why we prefer high-level languages like C, C++, or System C to create functional models. And then you need to understand how we create a register transfer level model, synthesizable model in HDL. You can choose either Verilog or VHDL. And whatever the synthesizable model you create, how you can synthesize that into netlist, and then how you can implement the circuit. Basically, you need to take the netlist through physical design flow, floor planning, placement, routing. So it goes through various steps, and then finally we produce the routed netlist, GDS2. So engineers who come to Maven Silicon, they understand everything about the design flow. That's what actually they are going to learn as part of this course. But why smartphone? We give this smartphone as an example. Basically, engineers want to understand the big picture, how they can apply VLSI to realize any complex device like smartphone. That's the objective of using smartphone as part of our course.
Right. I think we've come to the end of today's episode. It was a very, very insightful session. Thank you, Mr. Sivakumar, for spending your time. I've learned a lot today on how binary language works and how we make apps in the smartphone and how exactly a smartphone works and how VLSI is involved in it. So thank you for today's session. And we are closing with today's episode. And if you are still not quenched with your curiosity, do check out our Instagram page for live updates on our upcoming podcasts on ChatGPT, IoTs, and so on. Until then, stay curious and keep on harnessing the power of these smartphones.
Thank you.
Thank you.